Okay, good morning. We start now the first lecture of this morning. Mohammed Abouzaid from MIT. He's going to talk about on the symplectic topology of cotangent bundle.
Thank you very much, and thanks to everyone for cutting their party short last night so they could come here early in the morning. So I will be talking about problems in symplectic topology. And I'll be focusing on cotangent bundles, but just so that, don't want to assume that everyone knows what symplectic topology is about, let me just start with a very short introduction. So symplectic manifold is just a smooth manifold equipped with a closed two-form. We'll call it omega. And we have to impose a local condition, which is that if we take this symplectic, this two-form omega, and we take it to the top power, n is the dimension of the 2n is the dimension of the manifold. So if we raise it to the nth power, you assume that at every point you get a volume form. That's some sort of non-degeneracy condition. So there's the key question of symplectic topology was raised by Arnold in the late 70s and early 80s, and that somehow, you can condense the question to saying, what if you just knew the homology class of this symplectic form, and you knew the smooth structure on M, then would you know what this symplectic manifold is? And of course, that's one very silly way of saying it. You could also ask, for example, about maps, which preserve the symplectic form. If you have a map, and you know that it preserves the homology class of omega, can you somehow isotope it to a map which actually preserves omega strictly? Or you could ask about submanifolds. If you have a submanifold of your symplectic manifold, and the cohomology class of omega vanishes, can you actually make sure that omega vanishes at every point, and so on and so forth? But these are the key questions. Is there some sort of homotopy data that you can extract out of the symplectic form, so that you can then recover the question about pointwise condition just by kind of perturbing whatever objects you're studying? And the answer is no. And this was proved by Eliashberg and Gromov in the 80s. I won't say exactly what they said, the way they proved it, because it has to do with, they looked at it from the point of view of maps which preserve the symplectic form. They proved that that the set of maps which preserve the symplectic form is closed in a certain topology. But now we have had many results since then, kind of showing that really kind of just knowing the symplectic form is not enough. And one kind of example of the sort of results we can prove. This was proved by Mark McLean, and he never kind of published this, and also proved by Paul Seidel and I. And that says that if you look at symplectic forms in R2n, and you impose a certain completeness condition, okay, you don't want wild properties. You imagine a little bit like having a complete metric, even though symplectic forms don't have local invariance, but nonetheless, it's the right thing to imagine. Then R2n has uncountably many symplectic forms which cannot be deformed to each other. Okay? So you could almost say that the difference between smooth topology and symplectic topology is some uncountable amount. So today, instead of talking about these sort of problems, we'll go the other way. Let's start with some symplectic manifold that we think we understand. We have a very nice construction of it. And now let's ask some questions about it and see whether we can study the symplectic topology of this fixed symplectic manifold. Okay, now let's see how well technology works. I want to move down here, and I want to move up this way. Great. So what's the symplectic manifold that we'll be studying? So start with some smooth manifold. I'll call that Q. And you can construct a tangent bundle, but you can also look at the dual space, the cotangent bundle. That's T star Q. Locally, it has these coordinates, just useful to write down. The base is Q. The fiber is P. And there is a form on this called the Liouville form, which is sum of pi dqi. Essentially says evaluate fibers along the base tangent vector. And the differential of this form is a symplectic form. So that's when I say the symplectic topology of a cotangent bundle, I really mean, look at this specific symplectic form on the cotangent bundle. So just, again, so that we have some examples in mind, if I started with the circle, the tangent bundle is trivial. Okay, so topologically, I have S1 cross R. Now, in dimension 2, a symplectic form, that's just an area form. Okay? So I have some area form on the cylinder, and it turns out that this area form is the one that has infinite volumes, infinite area at both ends. Okay? It's just a cylinder extending continuously, from here all the way out there. So now, this is the symplectic manifold we'll be talking about today. I'll be trying to say some things about it, about what we know about it. Great. So this is a conjecture of Arnold. I'm not stating it exactly the way he did. Well, first, I'm not stating the way he did. So the conjecture says, you take your smooth manifold Q, and if you understood the symplectic topology of the cotangent bundle of Q, then you could recover the smooth structure on Q itself. Okay, so there is this, call it a functor from some smooth manifold to symplectic manifolds, which is passing to cotangent bundles. The claim is that this functor remembers everything about the smooth topology. So in order to say precisely what Arnold said, I had to introduce a new notion, which is that of an exact Lagrangian submanifold. So, Lagrangian is said to be, so a Lagrangian is always going to be half-dimensional. So for example, if I take the zero section in a cotangent bundle, that exactly has half the dimension of the total space. So an exact Lagrangian is one such that if I take this one form lambda, this thing that defined the symplectic form, and whose differential is the symplectic form, and I restrict it, then I get something which is zero cohomologically. So first it has to be closed, and moreover we require that it's exact. That's why it's we call it an exact Lagrangian. So there's quite a few examples. So for example, you can take the zero section, as I said. The reason is that you look at these. The zero section is somehow p equals 0. Okay? And if I take this form and I set p equals 0, then indeed I get 0. So that's why the
So Lagrangian means the form is closed.
Yes, Lagrangian means absolutely. So now let's see how well technology works. So that was the zero section, which I drew out here. Now one thing you can do is you can take any function and take the differential and then draw the graph. And this is not working. Let me just. Okay, and you can draw the graph of the differential of a function. I drew one over there, and that's also going to be exact. But there are plenty of Lagrangians which are not exact, and this is easy to do because I'm working in dimension 1. For example.
But that was not exact.
Why is it not exact? Because there's not enough area.
Right.
Okay, sorry.
Got to go down more.
I've got to go down more.
More than that.
Okay, better? I know, the area above and the area below have to be exactly the same. So, okay, let me draw something that is not exact, just for Dennis's. To make the point even clearer, this is not working. Yeah, there we go. This will work. So if you take something which is somehow raised off the zero section, then that will not be exact. But another example of an exact Lagrangian. This is not working for me, so I have to use the blackboard. Another example of an exact Lagrangian is that you can take a point and you can take the cotangent fiber at that point. Okay. So the reason that that's exact is because the form is sum of pi dqi. This thing only corresponds to p variables only. I restrict dqi to this, I get 0. So this is also exact. And again, one last example of something that is not exact, well, that's this circle. Okay. This circle over here cannot be exact. And the reason is some version of Stokes' theorem. Okay. So if I take lambda and I try to integrate it over the circle, okay, then if the circle happens to be the boundary of a disk, such that this one, then this is the integral of d lambda over the d2, and this happens to be the area of d2, and this has non-zero area. Okay, so that shows that lambda is not zero cohomologically. So, so that's the reason we're going to study, or the reason kind of Arnold is going to make a conjecture about exact Lagrangians is because there's too many non-exact ones. Okay, there's this one right here. There's one in every kind of small chart. You can just draw tons and tons of non-exact ones, but exact ones should have some sort of rigidity properties. And the conjecture is down here, and it says, if you take a closed smooth, if Q is a closed manifold, okay, and you have a compact exact Lagrangian, which we call L, then necessarily L is isotopic to the zero section. That's the zero section over there. So, well, if they're isotopic, then they better be diffeomorphic. Okay? And that's how you go. You kind of go from this conjecture, which kind of Arnold actually stated, to that conjecture up there. This conjecture tells you that there is exactly one smooth diffeomorphism type of a closed exact Lagrangian inside a cotangent bundle. And so this theorem is true for the circle, because you can just draw pictures. And it's also true for S2, and this is a result of Richard Hine.
About a circle that has half its area below and above, and there's no homotopic.
I don't quite know what you have in mind, but
Move that circle down until
this circle.
Until it becomes exact.
This one?
Yeah.
But this is not exact. I mean, the obstruction to exactness is whether it bounds, if it's null homotopic.
Oh, it's the area.
Exactly, it's the area.
Oh,
okay. And the point is that the exact form tells you that even if it's not, the fact that you have this primitive lambda tells you that even if it's not null homotopic, you still have some notion of how much area does it bound. It's just how much area does it bound relative to the zero section. So it's not closed. So I said if L is compact exact. So this theorem is also known for S2, and the proof for S2 uses very, very special techniques from four-dimensional topology. How you take the cotangent bundle of S2 and you observe that this embeds inside P1 cross P1, and then you study holomorphic curves on P1 cross P1. And this sort of analysis that you do, it doesn't really work it doesn't work beyond dimension 4. So these are the only two manifolds, S2 and S1, for which this result is really known.
And two manifolds in the cotangent bundle could be knotted or quite complicated, right?
Yes, so this result essentially says there is no knotting of Lagrangians inside T star S2. Okay, so let's move on there, and let's. So what I want to explain is much of the talk will be explaining the following results. Sorry, a little bit of the top is cut off. Let me just read that sentence. So if you have such a closed exact Lagrangian, just like over there, inside the cotangent bundle, then in fact it is homotopy equivalent to the zero section. Okay, so this result is an extension of some results of David Nadler and the Fukai-Seidel-Smith, which essentially proved that the cohomology groups are isomorphic. So this sort of technique I'll describe kind of allows you to kind of deal with pi 1 without having to worry at all, and actually prove that you have a homotopy equivalence.
Pi 1's not a problem?
Pi 1 is not a problem. I mean, you can ask me, you'll see at some point, you'll be like, how can you deal with pi 1? And then I'll tell you it's not a problem. Okay, so what's the main tool that I'm going to use to prove this theorem? Well, something called the Fukai category. Okay, so what is the Fukai category? Well, it's some category associated to the cotangent bundle. Actually, it's associated to every symplectic manifold, but might as well just work just in this setting. Its objects, for me, are going to be exact Lagrangians. I just told you what those were. And I want them, if they happen to be closed, then everything is OK. But if they're not closed, then I want them to be well-behaved at infinity. There's some condition called the Legendrian condition. That's what I mean by well-behaved at infinity. And moreover, I want to equip these objects with local systems. And that's why we can address the fundamental group problem, because if you have non-trivial fundamental group, then you just take any local system, non-trivial local system, and then that'll give you an interesting object of your category. Great. So those are the objects we study. So what are the morphism? Well, there is this invariant called Floer cohomology. Okay, so what is Floer cohomology? So again, the pithy way of saying it is a categorified intersection number. But what it means is that for every pair L1 and L2, I'm going to define some chain complex, which is called CF star of L1 and L2. Okay, and what it's going to be generated by the intersection point L1 with L2 prime, where L2 prime is kind of transverse, is somehow a deformation of L2, which is transverse to L1. So perturbation.
What are the appropriate deformations in exact Lagrangian submanifold?
They are the deformations as Lagrangians which preserve the exact condition.
Perfect.
But in practice,
Analysis of my question, just turn it around and get the answer right.
yes. in practice, Hamiltonian isotopy is the thing that has this property. But that's why Hamiltonian isotopies are good, because they preserve it. Yes. So L2, so perturbation of L2, which makes it transverse. So intersection. Okay. So there's some you form some chain complex with this basis. It's a little bit of care what you do at infinity, but we won't discuss that too much here. And then you want to define a differential on this complex. This is a set of morphism. You want to define the differential, and the differential count holomorphic curves. So I really don't want to go into the details, but count holomorphic curves means count pictures like this. 0, and a picture like this tells you something like that d of x1 is equal to x0. Okay. Well, that's the case if this is the only holomorphic disk around, and if there are many of them, you're going to take some sum. And the sum is going to be over all holomorphic disks. So similarly, there's a multiplication. The multiplication takes into account not these, these are called strips, actually, but it's going to take into account polygons. So now I have L1, and I have L2, and I have L3. And I'm trying to ask myself, I take x and y, which are generators here, and I multiply them together. What coefficient of z here do I get? And then it's obtained by counting, again, holomorphic curves. They solve some Cauchy-Riemann equation with boundary conditions along L1, L2, L3, and kind of corners along these three guys. It really is coming. You have to solve this PDE to get the answer. Now, there's one fundamental property of the Fukaya category that actually allows you to do some computations. And that's the thing that I pointed out here. So if you have a closed Lagrangian, okay, not something that goes out to infinity, something compact, you have a local system on it, then you can compute the endomorphism algebra of this object of the Fukaya category. That's how the Floer cohomology between this object and itself thought of as an object of this category. And it turns out that that has a classical answer. Okay? And the classical answer is you take this local system, and you take the endomorphisms of it, and you compute the cohomology of your Lagrangian manifolds with coefficients in this local system. And this has a generalization. I mean, just an obvious generalization. I take E, and I replace it by E1. I take the second E, I replace it by E2. And again, you can compute over here. And this is extremely special to the exact case. Okay? In general, if we were doing symplectic topology not in a cotangent bundle, or if we were studying Lagrangians which were not exact, then we would not have this isomorphism. We would have a spectral sequence. Spectral sequence goes from here to here. Okay, there would be some corrections to this. So now, the reason I mentioned this is because this is the key idea for how you can use symplectic of the Fukaya category to make statements like the one above, the one about homotopy equivalence. Okay, so let me now tell you the strategy for how you get there. Okay, so the strategy is like this. You have your symplectic manifold. It has all these Lagrangians, and you're curious about them. Okay, but geometrically, you have a lot of, you can construct a lot of them. But if you say, let L be an exact Lagrangian, you don't know how to get specifically to the geometry of this unknown Lagrangian. But what you hope for is that you have a collection, a family of Lagrangians, which you understand very well. Okay, let's call that family LP, and let's call it parametrizing space P. And then there should be some reason why, if you have enough of these, then everything else should be determined just by this collection. And this is actually a geometric condition. The geometric condition goes like this. Take your family of Lagrangians. Take all holomorphic disks with boundary on your family of Lagrangians. So if you take such a...
On a member of your family?
Pardon? On a member, yes. So this is kind of a parametrized problem, parametrized Cauchy-Riemann problem. So take all such holomorphic disks. Whenever you have such... So imagine this picture. So here's Lagrangian. Here's a holomorphic disk. Okay? So whenever you have such a holomorphic disk, you can evaluate at somehow an interior point. So evaluate at all possible interior points. So you get some cycle. You get some cycle in the space. And the assumption that you want to make is that this... Pardon?
Script P is a cycle.
Well, yeah, sure, yes. Let's say it's
Oh, because the set of Lagrangian disks form a cycle.
yes. The set, so it's there's something coming from P. So assume P is a like closed manifold for now, and the set of Lagrangian disks itself forms a cycle. So kind of together they form some like a D2, yes, some cycle in the space. And you assume that this cycle actually is the fundamental cycle of your symplectic manifold. Okay, so that's essentially the way I said it over there. Is that means that if you look at this moduli space and if you fix a point in your if you look at your symplectic manifold and you fix a point in your symplectic manifold, then you can find some disk passing through this point, some holomorphic disk passing through this point, whose boundary lies on one of the Lagrangians that you were studying, on one of your Lagrangians that's a member of your family. So this is some geometric condition.
It's algebraically unique or some
well, you know, somehow the real truth is that there isn't exactly one, that if you count them correctly, that the number is one. And this, I mean, you know, this is like a philosophy, and then you have to realize how to interpret this using algebra. But this is the philosophical point. Now, once you have this, then everything comes down to algebra. So if you have this condition, and if you're trying to understand what is the set, what is, from the point of view of Floer homology, from the Foucault category, what do all exact Lagrangians look like, then it comes down to understanding the Foucault category whose objects are these Lagrangians parametrized by this space that you're studying. And it comes down to the following very specific question, which is, look at this category, FP, consider modules over it. Okay? So in particular, consider modules of bounded homological dimension. Why is it bounded homological dimension? Because
Can you sort of say this point that this kind of category is like in algebra, so you can talk about a module over it?
absolutely. So drop the word category and insert the word algebra, and then just think about modules over an algebra. Okay? If I have modules over an algebra, they have, except that they're kind of graded modules. Okay? So they live in some homological degree, and because the objects you're interested in studying come from closed Lagrangians, well, Lagrangians, they have finitely many non-trivial cohomology groups. So that's going to be reflected in the fact that this module that you're going to be studying, it has bounded homological dimension. And moreover, if you look at the endomorphism algebra, I told you in the slide that the Floer cohomology of a Lagrangian who comes to the local system is isomorphic to the cohomology of L with coefficients in this local system. Well, this is supported between degrees 0 and n. Okay? So it better be that your modules are supported between degrees 0 and n. Okay? So this geometric condition allows you to translate looking for Lagrangians that satisfy this property into looking for modules that satisfy this property.
So you're trying to go from the LP special case of Lagrangian to find the rest. You try to find them in an algebraic way by these considerations.
Yes, you find them in an algebraic way by thinking of them as modules over the algebra associated to the script LP. Any questions? Okay, so somehow it looks that this is a very disconnected story. At the top, I tell you, look at holomorphic disks and make sure there is enough to satisfy this property. And at the bottom, I tell you, do some homological algebra. So there has to be some sort of link between these two. And this link, the link between these two is given by something called the cardi relation. Okay, so fortunately, okay, so what does the cardi relation say? Well, something that physicists know. So this is some sort of homological interpretation of the cardi relation. So let's assume, for simplicity, that I said take a family of Lagrangians. Let's assume that there's just one of them. Okay. So the condition I said above says that I imposed that condition over there, the one about the moduli space, blah blah blah. What it says is that if I look at this fixed Lagrangian and I look at all holomorphic disks passing through this, then there exists one such thing counted with multiplicity passing through every point. That's what it says. So this is my script L, and now I have some other Lagrangian. Let's call it not script L. Okay, it's over there. And I fix a point on that Lagrangian. Okay. So my condition has been that there exists some holomorphic disk passing through this point. Let's call this point E of L. Okay. So now there exists another disk which we can consider, which doesn't have boundary on script L, but instead has boundary on Roman L. That's a constant disk which maps to EL. There's always such a disk. You take this constant disk, and what you can do is you can glue this disk to this disk at this point. Okay, this is an interior point of the disk with blue boundary, and I can glue it to this interior point of the constant disk with red boundary. I glue them together. And when I do that, let me just draw a picture. And some of the other guy is very small. It looks something like that. But you glue them together, and what you get is what, holomorphic curve theory tells you. You get something like this with a very, very thin neck. So, and you have a marked point here. Important to keep track of. So now, if you think about what's happening from the point of view of the source of this.
Is this the annulus in Kenji Fukai's talk?
Yes. This is the annulus that's in Kenji's talk. Okay. Absolutely. If you think about the source of this map, you can alternatively think of it as, instead of drawing this picture, what you can do is you can draw an annulus with extremely long modular parameter. Okay? As this modular parameter goes to infinity, what happens is you get a half-infinite cylinder in this direction and a half-infinite cylinder in this direction, and a half-infinite cylinder is nothing more but a disk with a puncture removed. Okay? So that's how you go from disks to annuli with large parameter. Now, if you have this modular parameter, you can then just shrink it to 0. Okay? Of course, if you do it naively, you think something bad is going to happen. You're shrinking this to 0. But in fact, when you
shrink it, how do you stretch it? How do you shrink it?
So you are looking at maps from some Riemann surface to your manifold satisfying a certain condition. But your Riemann surface, it has a modulus. So you just consider one-dimensional moduli space inside the source, so inside the abstract moduli space of Riemann surfaces, and solve an equation for every such. And then you get a cobordism between the set of solutions for this guy and the set of solutions for every modular parameter. So that's how you shrink. You just kind of solve an equation. You change the modular parameter in the source and solve an equation that varies smoothly in the modular parameter. So when the modular parameter reaches 0, you have to be careful. There are different ways that you can achieve this degeneration. But one way you can achieve this degeneration is that your annulus, it breaks into two disks, here and here. Now you can see how I can recover an annulus from this. If I were to kind of smooth this node a little bit and smooth this node a little bit, I would get an annulus. You would, here's the boundary. Here's the kind of the blue boundary around here, and the red boundary is around here. Okay. Great. So let's note one thing. We started with this script L, this blue guy, and this Roman L, this red guy, and we didn't know anything about their intersections. Okay? All we knew is that there was some holomorphic disk here with, that passes through this. But now, when we go through this degeneration, over here, what are these points? These points must be points where L, script L, and red L and blue L intersect each other. So you immediately conclude that this script L must intersect this blue L. So this condition about, the first thing that this condition implies about a holomorphic disk, the first thing it implies is that every Lagrangian must intersect one of the members of this family that you were studying. But in fact, it implies much more, because you just have to do some homological algebra. So what you do is you take this picture over here, okay, and you completely ignore this left-hand side disk. You only look at this right-hand side, okay, the right part of the disk. And what is this right part of the disk? Well, I told you over here what to do. Let me just redraw some things. This is exactly this picture, except that everything is relabeled. So this picture is this picture over here, except that this is script L. Okay, this is the thing that here I call F. This is the thing called G. Okay, this is L. This is L, and this is this guy E of L. Okay, and of course over here they're transverse, and over there they're not transverse, but that's not a big deal. Now, what was this picture illustrating earlier? It was illustrating the product in this category. This picture says F times G equals EL. Okay, F times G equals EL. Well, if f times g equals EL, then that means that the red guy, the other way.
Wait, why does EL intersect itself?
So that's exactly, so
Why does L intersect?
the difference between the two pictures is like this. Over here, this boundary component and this boundary component are exactly the same.
But wait, L
We're
is
at-
supposed to be an embedded Lagrangian. I don't understand the drawing.
You're absolutely right. So here's what happens in Floer theory. So what I drew earlier was like this. There was L1, L2, L3, and this was an intersection point between them. What I'm saying is that when L2 is actually equal to L3, the way you should interpret such an intersection point is just as a cycle inside L. So that's the picture we have.
You mean L3 is a perturbation of L2 in this case?
Yes, L3. If you can, if you know, I can make this.
Right. Okay. Fine.
And then you would have exactly the picture you want. Okay, so we have this equation, f times g equals EL. Okay, but this is an equation that people know very much from linear algebra. If I have a vector space U and a vector space V, and I tell you there exists a map here called F and a map here called G, such that, okay, I guess I didn't know. Let's do F and G, such that F composed with G is equal to the identity of U. Okay, then you would immediately say, well, this is a sum end of this. That's exactly. This is an inclusion. This is a projection. Composition of the two things is the identity. So this is a sum end of that.
No, the other way around.
No, this is the sum end of that.
Yes. No. Yes. Oh. But he said F first.
I'm sorry. I don't quite know what to say.
listening to what
You
said.
first go to G, and then you.
No, not what you wrote. Okay.
I'm sorry. Yes. Well,
You wrote something and said the other. Okay.
I guess I should you compose by doing the first. Yes. Okay. G composed with F. Is that what you want me to say?
Yeah.
Anyway. Okay.
Right.
G composed with F. So that says that what did I say again? This is a sum end of this. Okay. Now the same thing is true in the Fukaya category in a categorical setting. You just have two objects of some category, in which the notion of kernel and co-kernel makes sense. The notion of sum end is really what we need here. And if you can find F and G such that F times G is equal to the identity of one of them, that means that this L here, which is the red L, which is the guy that we didn't know about, is in fact the sum end of this script L, which is the blue guy, which is the guy we knew about. So, in practice, this almost never happens. This condition that, the moduli space interpreted this naively, has multiplicity 1, but you just now put some fancy algebra, and you generalize this much further, and you get some condition under which the Floer cohomology of every Lagrangian can be just understood by understanding modules over the Floer cohomology of this script guy. Okay. But this is the essential point. Okay. Any questions? Great. So now I will say just a few words about how one can actually apply this to the case of cotangent bundles. Okay, so I should tell you about a nice collection of Lagrangians which satisfy this property. Well, there is one easy such choice, and that's the category consisting of all the family consisting of all the fibers. Okay? If I look at my symplectic manifold, it is the union of all the cotangent fibers where I let the fibers vary over all points. And in this interpretation, I must talk about holomorphic disks, but at every point of every cotangent fiber, there exists a constant holomorphic disk. Okay? And if I take the union of all these constant holomorphic disks, there's one passing through every point. So they satisfy the condition that I told you earlier. Okay? So that means that if I take any unknown Lagrangian, which God knows how it was constructed, this kind of cardi relation result, this annulus argument, tells you that really what you should need to do is you need to understand the category of modules over the Floer cohomology algebra of these cotangent fibers. So we must say something about that algebra.
So there are no other disks besides this constant
Well, it depends exactly how you do it. So, I mean, the correct answer is there are no constant disks. It's exact. There's no other disk other than the constant one. The fiber is exact. So really, this is all there is. So, yeah. Great. So now we're down to understanding the Fukaya categories. Objects are the cotangent fibers. OK, well, now there's some choices to be made. And there's actually several flavors of what the Fukaya category in the presence of non-compact Lagrangians is. And I'm going to kind of highlight the one that has some connections to string topology. Okay? So the answer is, if you use the one we call the wrapped Fukaya category, then what you get is that all the fibers are isomorphic to each other. And moreover, the endomorphism algebra of any one of them is just the chains on the base loop space equipped with the Pontryagin product. Okay? So this result was actually proved by Abouzaid and Schwarz and Portaluri. No, I think just Abouzaid and Schwarz. The level of homology. So this was that result. Abouzaid, Schwarz. Although I must say that, this is proved that homology. Okay. So what's the intuition behind such a result? Well, the intuition is that the sort of flavor of Floer theory you want to do is that when you consider a cotangent bundle, okay, and you have some Lagrangians that are not compact, then you must decide what to do at infinity. Okay? And on a cotangent bundle, that if Q has a metric, Q is a Riemannian, then there exists a canonical, what we call Hamiltonian function, canonical flow, coming from a Hamiltonian function, and the flow is the geodesic flow. Desic flow on the tangent bundle. And then you identify the two using the Riemannian metric. So if you use this flow, then it turns out that somehow the generators of the Floer complex are isomorphic. The generators of the Floer complex are the same things as base geodesics from this point to itself. Okay, so there's a correspondence between base geodesics and generators of the Floer complex. And then there's some difficult analytical problem in checking that the differentials that you get in Floer theory agree with the sort of differentials that you would get in Morse, in some sort of Morse theory of the base loop space, so that you actually get the isomorphism with these, with the homology of the base loop space. So that's the homology level statement. And kind of because everything that we do is derived, everything is at the chain level, turns out you have to be a little bit careful, a little bit more careful, and it's not enough to know this level of homology. But nonetheless, you can prove that at the A infinity level, the A infinity endomorphism algebra of the cotangent fiber, as coming from Floer cohomology, is equivalent to this differential graded algebra, chains on the base loop space, equipped with the Pontryagin product. That takes a little bit of fiddling, but it's not that hard once you know this result of Abouzaid and Schwarz.
When you say use the canonical flow, how do you use it?
Yeah, absolutely. You use it and you define. So I had some sort of definition of the Floer complex. There we go. And this L2 prime, instead of being blah, blah, blah to make it transverse, you say L2 prime is equal to the image of L2 under the geodesic flow. Yes, and then kind of small perturbations of the geodesic flow to ensure transversality. So you do some big deformation at infinity. Let me just draw a picture. Might be helpful. So you can, start with this Lagrangian, and I want to compute the endomorphism algebra of this itself. So I apply the geodesic flow, and what that looks like is like this. Okay. So what used to be something very local happening near this point is now knows about the global topology of your base. And in this case, the key point is that this is a symplectic. This depends only on the symplectic topology. You have to prove this. We use the metric on the base to write down this flow, but ultimately the answer, the homology group, or rather the chain complex up to A infinity equivalence, does not depend on any of these choices.
Like time one or something?
Time one flow, yeah. The time one.
Just let it flow for time one.
Yep.
So it flows faster.
Faster as you go up in the fiber. Yes. Okay. So, so now this brings us, so the strategy then said once you understand this algebra that you're studying, this Fukaya category whose objects are the Lagrangians that you understand as opposed to the ones that you don't, then you get to all the other Lagrangians by studying modules over this algebra. And there's actually a structure theory for such modules. Okay? And ultimately, the structure theory comes down to one very simple fact, which is that this algebra is supported in non-positive degree. Okay? So because this algebra is supported in non-negative degree, the following result that I'm asserting here is true. That is, if you take any module, okay, such that Hom from, well, the algebra to it is 0 for some sufficiently large number, Hom k, so this is I always have homological grading in mind, then you can actually filter it. Okay? And the filtration, it comes from modules supported in 1 degree. But moreover, if you look at modules supported in 1 degree, then those all come from the following construction. You start with chains on the base loop space. You map to the group ring by collapsing everything that is not in degree 0. And then you take just a representation of this group. Okay? And that constructs for you a module by pulling back. Great. So now let me just.
Result from Eric Malm's thesis.
Yes, this is.
Just that piece right there.
Yeah, this is a small piece of Eric Malm's thesis. But I think in this form, I mean, the first time I saw this was in Dwyer, Iyengar, and Greenleaf's. But absolutely, there's seed there. So, what did I mean to say? Oh yes, I mean to kind of just give you some idea of how you complete this story. Okay, so in fact, so there's this structure theory for these modules, and now let me go back. Oop, they're on the same slide. I didn't mean for them to be on the same slide. Let's go back to what I said. What we need to do. What we need to do is we need to classify all the modules whose endomorphism algebra is supported in degree 0 to n. Okay, that's what we need to do to kind of look at things that look like Lagrangians. And if you actually go through this construction, there's a very simple spectral sequence argument that tells you that none of these modules have that property, except for the ones that except for the ones that are kind of one piece, only have filtration consisting of one piece. That is, except for the ones that actually come from representations of the fundamental group. Okay, so this says if you're considering a cotangent bundle and you have some unknown Lagrangian equipped with some local system, we'll go back to that in a second, then the endomorphism algebra of this, the Floer the cohomology of your unknown Lagrangian with coefficients in this local system must be isomorphic to the cohomology of some local system on the base. Okay? Now, let's assume for simplicity the base is simply connected. Okay? That means that this Lagrangian.
Is V finite dimensional for some reason?
No. So that's the point. So that's the point. The point is that you do not require V to be finite dimensional. So if your base is simply connected, the only local system your Lagrangian could possibly have is a trivial local system. Because if it had non-trivial fundamental group, then the group ring is a non-trivial local system. And that's excluded by this analysis. So in order to do this, you must actually kind of work out Floer theory in the presence of these local systems of infinite rank, but that's not a big problem. I think we'll be back in 1 second. Okay. So let's use this guy while we have him. Okay, we have him. So, and then you can, of course, that was the argument when the base is simply connected. You could say, what if the base is not simply connected? And the answer is you pass it the universal cover, and then run the same analysis there. So
that was fast.
So I told you some answer when the base was simply connected.
Yeah.
There's no local systems. But if the base is anything, I can always pass to the universal cover, and then there's no local systems in the universal cover.
Not compact anymore.
It's not compact anymore, but you can still do Floer theory. And so essentially everything that I've said goes through without any problems.
But what are you going to achieve in this substrategy?
So this proves this actually absolutely. So what I've said now proves exactly this this theorem, which is that the inclusion of every Lagrangian every closed exact Lagrangian inside the closed cotangent bundle is a homotopy equivalence. And you achieve this in the simply connected case by telling what I told you, in the non-simply connected case by really passing to the universal cover and doing the analysis there. Okay, so
and then using other people you said proved homology isomorphism in some cases.
Yeah, so this strategy kind of encompasses those proofs as well. You don't really.
Okay, I don't see that. Why do you get homology isomorphism?
So what you get, so the homology isomorphism is very easy. You take your closed exact Lagrangian, the one that you don't know about. You equip it with a trivial local system. Okay, so that closed exact Lagrangian has an endomorphism. So the Floer cohomology of this closed exact Lagrangian with itself is isomorphic to the Floer cohomology of this, to the ordinary cohomology of this unknown Lagrangian. But it's also isomorphic to the endomorphism algebra of some local system on the base. Okay. It turns out the only local system this can be is the trivial local system. So you conclude that the two cohomology groups are actually isomorphic. Your unknown Lagrangian has the same cohomology group as the one in the base. And then you just you want to make sure this is actually induced by this inclusion map. And there's a natural map between them. Okay. Ultimately, the point is that you prove they're isomorphic in the Foucault, the equivalent object in the Foucault category. And that's strong enough to imply that this isomorphism is not some abstract thing, but it's actually induced by the map. So, okay. So they essentially sketched the theorem about homotopy equivalence, and really kind of the proof kind of subsumes the result about homology isomorphism. So let me say a little bit about one of them time. What else is there? Okay, so great. So this Foucault category, it's not there's some sort of A-infinity structure, but there is more stuff floating around, and that's what's called this extended topological field theory. So over here, I wrote down kind of the topological field theories we know. So the ones in gray are the ones that are obviously there, but if you ask me to give you a precise definition, I would hesitate a little bit. So there is obviously one coming from studying Floer cohomology in the cotangent bundle. Okay, that's just set up all the operations and everything works out. And then by work of Lurie here, if you look at the homology or chains on the base loop space, then that's some sort of Calabi-Yau algebra. I probably should have put Malm's name there as well, because working out exactly what this Calabi-Yau structure should mean. So then there's some classification theorem of topological field theories, and therefore you have one associated to the homology of the base loop space. Yeah. So now there should be two more, and all of these things should be isomorphic, but there should be two more. So one of them is associated to string topology. So the reason I put it in gray is because, setting up all the operations in string topology requires dealing with some transversality problems, and we know that we should be able to deal with it, but it's not kind of, it's not there, so you can actually quote it if you want to quote everything you want to quote. And similarly, over here, the construction requires this notion of Calabi-Yau algebra, and it's obviously true that the Floer cohomology is also of the cotangent fiber is also Calabi-Yau algebra, but again, to get everything right and get all the T's crossed and I's dotted, we're not quite there yet. So nonetheless, there is a lot of work, starting with work of Claude Viterbo, which proved that the symplectic, some invariant called symplectic cohomology is isomorphic to the homology of the free loop space. Going on to work of Abudandlo and Schwarz, which kind of did this thing with the base loop space that I mentioned, and anyway, many other people since then. So we have maps between these things, and so therefore we expect that all the operations that come from the topological field theory that you see in the Floer side, they agree with the ones you see on the string side, and moreover, they come from this Calabi-Yau structure on the base loop space. And that's supposed to be some sort of homotopy invariant of Q. Okay? But the point is that this is not everything. Okay? Not everything is covered. Not all the operations we could care about are covered by this picture. For example, and this is work of Lenny Ng, he doesn't say it like that, but this is how you can interpret it in this language. On the Floer cohomology of any Lagrangian, okay, there is an operation. There's a coproduct. Okay? We've been using only product, but there's also a coproduct. It comes like this. This is an input, and these are the outputs. Okay? Now, it turns out that this is highly degenerate. And more precisely, what happens is that there's always a map from the ordinary cohomology of every Lagrangian to its Floer cohomology with itself. Okay? And it turns out that this coproduct, it factors through the image of this map. Okay? That's exactly what I mean by it's highly degenerate. But because it factors through the image of this map, you obtain a secondary operation on the cone. Okay? And the secondary operation is obtained by counting curves. I think of it as solutions to some Cauchy-Riemann equation, which kind of interpolate between this Riemann surface and this Riemann surface. Okay? So that's a secondary operation. And Lenny Ing showed that if your manifold is, if your kind of cotangent bundle is the cotangent bundle of the three-sphere, and your Lagrangians are the conormal bundle of a knot, then you can use this invariant to detect the unknot. Okay? So there is something in there which is not purely homotopy theoretically invariant. Okay? If you take two knots, they're just homotopic as each other, as maps from the circle to S3. But this secondary operation knows something more, something beyond that. So still, knots in S3. That's really cool, but it's not. It's like the difference between like homotopy theory and like topology and linking numbers. You want to say something about Arnold's original problem, something about smooth structures. So so we only have one result about this in symplectic topology. That's the following result. So let's now talk about exotic spheres. Don't have that much time. It's okay. So the result is as follows. So you look in dimension 4k plus 1. So, okay, where k is not equal to 1. So 9, 13, so on and so forth. And you consider there are homotopy spheres in this dimension. That is, there are spheres which are homeomorphic to the standard sphere, but not diffeomorphic to the standard sphere. And what we can prove is that if you could embed such a homotopy sphere as a Lagrangian in the cotangent bundle of the standard sphere, then automatically this Lagrangian must bound a parallelizable manifold. Okay? So in particular, that tells you that if you could find some exotic sphere that does not bound any parallelizable manifold, then its cotangent bundle is very different from the cotangent bundle of the standard sphere, because the cotangent bundle of the exotic sphere has a zero section, which is, doesn't bound a parallelizable manifold, but the standard sphere has this property. So that's one thing you get. And of course, you want to make sure that this theorem isn't stupid.
But you've got to be pretty smart to follow all the implications. You're saying if the exotic sphere cotangent bundle is symplectomorphic to the standard sphere, then the exotic sphere gets embedded.
Yes. So if you have a symplectomorphism here, then what you can do is you can take the zero section and you can embed it in here. And now you have this embedding of this zero section as a Lagrangian inside here. And this theorem tells you that this Lagrangian would bound a parallelizable manifold. But we know that there are some exotic spheres which do not bound any parallelizable manifold, closed parallelizable manifold. Absolutely.
Well, half of those dimensions don't a priori.
Yes. So there's like a Z mod 2 that detects. Mm-hmm. So unfortunately, the proof of this result uses techniques that are completely different from everything else that I've mentioned so far. So as I briefly say over here, you're going to use the hop fibration. So you're going to use the fact that if I take S2n plus 1, then it embeds inside, well, of course, it maps to CPn plus CP2n. I guess everyone knows this.
You wrote 4 then?
I put 2.
Oh.
That's always true.
Yeah.
No, it doesn't embed. It just maps.
Oh, it's just a map.
That's the hop vibration. But now, it's...
Hop vibration.
You don't want to call this the hop vibration? If I let...
Dimensions are funny. I mean, CP2n?
CPN.
Okay.
Thank you. So there's a map. It's called the hop vibration. Now, I can want to turn this into a Lagrangian embedding, and you can turn it into a Lagrangian embedding by considering that. Okay? You can just turn the hop vibration into a Lagrangian embedding by considering that, and then you study the symplectic topology of this space here. Okay? So it's some completely different approach where you kind of just cheat a little bit. You're not using the cotangent bundle itself as much as you're using some other space. And it's out of this other space, and out of studying holomorphic curves in this other space, that you can construct this parallelizable manifold. So the only thing that so last night,
It's the same technology, sort of, to try category.
you don't use algebraic techniques. You don't use categories at all. There's no algebra. There is just solutions to the d-bar, to the holomorphic curve equation. And you really say there exists some moduli space with a boundary component, and the boundary component is the exotic spheres. They arise as constant disks, and you manage to make sure that this moduli space is compact. That's not very hard. That's some sort of Gromov compactness. That it is smooth. That requires some care, because usually these moduli spaces, it's very hard to show that their smoothness, and moreover that it is parallelizable. Okay, and then well, anyway.
Oh, so it's like the Donaldson original.
It's like Donaldson's, yes, absolutely.
Makes the thing bound.
By solving some equation.
Right. Oh.
Absolutely. So the only thing so last night, I learned that there's a student of Dennis who's been working on trying to understand what string topology has, answering Dennis's question for the last 15 years, trying to understand how much the string topology detects smooth structures. And so he has an approach, I don't understand very well so far, that can be used to distinguish lens spaces. And so the hope is that if one were to understand such a, so this uses string topology. The previous slide told you that there exists some very strong connection between string topology.
Same operation over here, I think.
Well, except that here I mod out by constant. It's an operation on the cone, whereas here, if I understand correctly, the construction. Okay.
Finesse that point.
Okay, you finesse that point. Yes. Okay, so you finesse the fact that over here there's a
same
point.
co-product with that homotopy between the two degenerate pieces.
I see. That's what you count.
Yeah.
Great. So to the extent that we can check that this construction is the same as that construction, then hopefully we would have more examples of cotangent bundles that we could actually distinguish. Okay, well, I will stop here a few minutes early.
Any questions or comments?
Is it possible? Is it possible to say just a few words about this? You mean the last sentence that you can use string topology to distinguish smooth structures?
I think it is best to let Dennis or his students say.
Okay.
There'll be a talk on that.
I won't be there, but anyhow, okay.
Two talks.
More questions?
I have a comment.
Yeah. What was it?
Wow.
So let us take the speak again and we'll come back.